Okay, so we'll go ahead and get started. It's about, I guess, 11:04. I guess that's NREL start time. So I wanted to introduce. Thank you for all coming. Thank you all for coming. And this is another edition of our seminar series. The point of these seminar series is because we have a lot of new research in the buildings program, and it really expands the spectrum of some of the outreach and impact that we've had. And these series are a way to really ensure that we're getting communication, because we as an organization, we may have bigger impact when we leverage the intelligence and momentum of the whole organization. So thanks for coming, so that we can so please feel free to look at it, critique. If Chuck is off base, let him know. But if he's doing well, just keep it to yourself. I'm sorry, I was supposed to say the opposite. That's what he told me to say, the opposite way. But so no further ado, I'll introduce Chuck. This project is really it's an exciting project that we were able to be funded by DOE. The buildings office asked us to look into what is the opportunity for next generation thermal energy research. There's been a lot in the existing space, but saying what can we do that's really never been done or really expands our current focus. And it took advantage of this big idea. It's called HEATR. I don't know if Chuck will get into that much, but it's a bigger idea, multi-lab initiative of HEATR, really kind of expanding. And so we took that and applied it to buildings, and Chuck is going to get into details. So to give you already know Chuck. He didn't give me a bio, so I get to make it up. I think he went to school somewhere. I don't know where, but he says he has a degree. I won't hold back because he has the mic after me. So with no further ado.
Okay, can everybody hear me? Hopefully. Okay. All right, so Router kind of introduced the idea a little bit, but HEATR, this is, in my opinion, the only good acronym that's coming out of DOE ever that I've seen. It actually kind of makes sense. Maybe RPE has some stuff, I guess, so whatever. But, okay, so kind of an introduction. So this is a DOE big idea. It's a lot bigger than just the stuff I'm going to talk about, but according to their websites, to challenge national labs to develop early stage, large scale solutions to national issues. So it's not just a one-off thing. It's meant to be really, really large. And specifically HEATR, looking at transforming the conversion, storage, transmission, and utilization of thermal energy, which is essentially as big as, it's like saying we're taking on the first law. I mean, that's kind of as big as you can get. So again, bigger than buildings, although that's all I'm going to deal with. That's all we're talking about in this particular project, which is just a subset of the bigger HEATR. And then we're collaborating with LBNL, so it's not just NREL. So I stole these slides from Robbie Froscher, who's the PI, so he's at LBNL. He presented these at the DOE Big Idea Summit, and I just shamelessly took them because he did a lot better job at kind of giving the big overview of the bigger project than I would. So the notion here is anytime you're dealing with energy, heat's involved in a big way. Doesn't really matter what you're doing. We all kind of know this. You can't really transform it. You can't really move it. You can't really use it unless you end up with a lot of heat. So no matter what you're dealing with, heat is involved in a really big way. Okay. And this is kind of a high level slide, but if you were to look at it from the source, in the U.S. energy use, maybe it's around 100 quads. Thermodynamic limits, Carnot, things like that, you end up rejecting maybe about 2/3 of that, and you only kind of use give or take 1/3. Okay. So no one's claiming necessarily that there's 66 quads that HEATR is going to utilize completely, but that's a really, really big target. So maybe it's worth thinking about differently rather than just rejecting it the way it always has been. So a little bit of detail. So the kind of the breakdown. So maybe roughly about 25 quads from power generation, another roughly kind of 25-ish quads from transportation, 5 in industry, and then they kind of have 7 in buildings. So I actually think this is really a little bit misleading because most of this power generation goes to generate electricity, which is then used in buildings, right? So this buildings number is kind of deceptively small. And really, I think even without that consideration, one of the things we're going to talk about is reducing loads and things like that. So I think it's actually a lot bigger than 7. Point being, really, really big numbers, thinking really big here, right? The challenge. So how do you manipulate thermal energy across all these complex systems to do something that actually matters to people? Okay. Again, this is a bigger project. some of the R&D needs that were identified at this Big Ideas Summit: transmission, storage, heat exchange. And I think that our subset of the project probably deals a little bit more with just a few of these, well, maybe half of them. So it's not necessarily trying to cover everything that you might care about in thermal energy, but in some way or another, you might touch on a lot of these. Okay, so this is, oh yeah, and then this is the last slide on this kind of big overview. You can see all the different kind of players and areas that might be involved. Huge part of the U.S. economy, blah, blah, blah. Okay. at this point deliberately ignored that. So I think that's probably a pretty small number, not zero, but that's pretty small. Dehumidification is a bigger deal. Did not get to that in here. So yeah, clearly, and when we're trying, again, this is the absolute biggest that you could make this number, right? And we're nowhere near that, and we probably realistically will never get anywhere near this, right? So trying to get a handle on that, and we just didn't have, to get to the dehumidification, I think is a lot more complicated to deal with at this more fundamental level, like what would be the absolute limit. So that's something that is duly noted is not here, but could be in the future.
Theoretically, you can have totally durable materials that will resist to mold and mildew, and you still actually keep a person comfortable. So that can be still. You have to have a mic. So you can still, as a theoretical max, right? You can still have every other material be mold and mildew resistant, but then you would still have to provide that theoretical minimal to people to keep them comfortable, because the building exists. If you're kind of familiar with PF, you can almost think of this y-axis as kind of this would be a cost-effective solutions for retrofits. So it's kind of minimal on your PF curve. But say that roughly speaking, a little over maybe 20% of the current thermal load could cost-effectively be reduced today. Okay? That just kind of gives a baseline, so you get some idea of where things could. Now, if you think of the horizontal axis here, yep.
What's the x-axis?
The x-axis, yes. So the x-axis is what the temporal load, which is really a little bit euphemistic for thermal energy storage. Okay. So this is this is normalized here. So So if you were to take energy that could be stored thermally in buildings, and then normalize that by the total amount of energy that's used, that gives you some fraction. Okay, so it's kind of normalized. And this is the, so if you were to say, I'm trying to give it out, but if you had, say, a gigawatt that was used in energy in a given situation, and you could thermally cycle, say, 200 gigawatt hours and megawatt hours through that, you'd be at 0.2. Right? So if this was one, all of the energy that you use would somehow be stored or cycled through your thermal energy source.
So 35% about what heat cold so far.
No. Well, it turns out that that's reasonable, but that was just kind of coincidental. So, if you were to look at currently in the U.S., about 2.5% of the energy that's used is cycled through energy storage currently, not thermal, just energy. Both that's pump hydro, right? So again, this kind of gives you a ballpark. You were out here at 1, you say all of the energy would somehow be cycled through storage, right? Where we currently are is kind of down here around 2.5%. That's approximately. The notion being, you can get some idea on where buildings exist today. Somewhere down here in this relatively small area, are things that could sort of happen today. They're plausible. This isn't really futuristic at all. Now you might argue about how many buildings are actually operating here, but it would be cost effective.
Now, this gets a little bit into your question. So, the next step after you back up, so after you kind of have some idea on where things are today, if you were to say, look, now if I have perfectly performing thermal energy storage in buildings, and I have as much of it as I ever want, no losses, you can accept as much power and and there's infinite capacity. You have way more capacity than you need. You're not limited by any of that. What would be kind of the maximum that you might be able to do in terms of what fraction of your total energy might be able to cycle through your energy storage system? And this is saying that now your grid is not changing. Down here on this axis, this is still today's buildings. Your buildings aren't really changing. All you're really doing is adding as much thermal storage as you possibly could, and then utilizing it to the maximum effect. And you might get around almost 30% or so of your energy might go through cycle to that. Okay. What you see on these lines as you move up is what you would do if you were to reduce loads through zoning. So we talked about this theoretical minimum amount of energy, which is kind of a maximum HVAC load reduction. Kind of moving along the way, all the assumptions there, but the idea would be that existing buildings kind of operate down here. With the current grid, you have an entire, all of this opportunity space could be available if you thought it was useful. Yeah.
So the orange line, that fraction of the original energy or the energy of the y-axis?
Yeah, it'd be of the y-axis.
So the 0.09.
Actually, no, sorry, that would be of the. I need to make sure I know that. That actually is of the.
The verification is now it's 30%-ish.
Yeah.
And then at the high end, 10%. That'd be 3 times less storage needed.
Right.
But if you're at the energy up here, then it'd be 30 times less energy.
Yeah. So actually, this is normalized by the original energy.
Okay. Yeah. 3 times less energy.
Yeah.
But you're actually using a much more significant fraction of that energy is going to storage.
Yeah. Yeah. So I have a line here, but there's a utilization factor.
It seems to me if you have perfect thermal energy storage, with no losses and infinite charging and discharging capacity. So if you had perfect thermal energy storage with no, you weren't concerned about capacity and you weren't concerned about you could charge and discharge capacity if you wanted, it seems like you could have 100% of your fraction going through your thermal energy storage.
So this is
This is for the thermal load.
Yeah. So this is normalized for total energy, not thermal energy.
Oh, okay. Yeah.
So that's what you end up being limited by. Is at some point your thermal energy. This is kind of a key limitation of thermal. Is if you store it as electrical, you can convert it to thermal if you want or not. All right. Yeah. Okay. No. Okay. Cool. Yes. So this is normalized by total energy. Now the next step beyond that would be, what if you actually had a more futuristic electric grid? So if this orange or red line, whatever it looks like, you have kind of around 8% of your electricity is generated from something variable, which is basically wind and solar. Doesn't include hydro or anything that looks a little more like base load, but good. But really more variable. Now, if you said the futuristic grid, it's around 70%. Right? So the futuristic grid, your buildings are kind of the same, at least down here near this zero on the y-axis. But your grid actually has a whole lot of variable generation. This might look something like California in 10 years, right? 15 years, something. 20. Buildings are pretty much the same, but you have a whole big change in your generation. So then the possibilities actually extend out, right? So there's a lot more need for storage in general. Thermal can pick up a lot of that.
I expect the thermal energy storage. You're throwing out some hydro, so it's not all thermal energy.
Sorry. Sorry.
The title on the x-axis that says TES, thermal energy storage.
Yeah.
These things on hydro.
So that does not include. So I am not including pumped hydro in terms of thermal storage. I was trying to, when I talked about this over here, this is not thermal storage currently. Currently, thermal storage is basically zero. I'm trying to give an idea or a flavor to people how much energy storage is really on the U.S. grid. So it's not really thermal, but it's just
the blue delta.
Yeah.
The way you're describing it sounds like that. Oh, we have all the variable generation, so we need all the flexible storage, but that's not thermal energy storage.
Yeah. So this would be if you have all the variable generation. There's a certain amount of energy storage period that's needed, and this portion of it could be addressed by thermal.
Just thermal.
Just thermal.
Not
Just thermal. Yeah.
storage.
The other storage is not shown.
Chuck, you say it isn't needed. What is your criteria?
Yeah. So
these aren't like theoretical maximums. These are criteria.
yeah. So the criteria I use. So the grid modeling that I did was relatively simple. I can talk about that a little bit. But basically, I said there's a certain amount of generation and a certain amount of load, and they got to add up to zero. And the model is on an hourly basis. So if you have excess generation, you might be able to curtail if you want under certain circumstances. But if you have excess load, it's got to come from somewhere, right? So that was basically my criteria for needed is your generation minus load has to equal zero, and that can include storage somehow. So I mean, it's fairly simplistic, but.
But how do you decide to break down the electric storage?
That's based on loads, which comes from red stock and/or Energy Plus models of. How do you to repeat that? How do you look or translate between electrical and thermal? How do you break that down? Those loads come from Energy Plus, basically, either through red stock or models of DOE commercial building prototypes. So you know what your loads are at any given hour, and you know the breakdown. So if you have excess electricity generation, you can either curtail or you can store that as thermal, or if really needed, you can store it as electric. Well, you convert it. There's a COP in there. You could do that. Or if you have additional needs, like you're short on energy, then if you have thermal storage and you have thermal load, you can use thermal storage to meet the load. Whatever else comes from something else. Clear as mud. Marcus doesn't count. Nah. Okay. So this is the kind of the paradigm for this. Okay. Hopefully this clearly did not go over well, but we got. I thought this was really clear. Okay. I worked really hard on this. But it's good.
To go on and then maybe
We'll come back to you. All right. So a little bit about the model. This is probably, for most people in this room, probably not too much of a stretch. But this is a model of power, so gigawatts needed for 4 days. The shades are different thermal loads in the building, and this red line is the generation over these particular 4 days. Just kind of random 4 days.
Across the country?
This is across the country. So I can break it down by climate zone. Most everything I did is national. So just to give, again, for people, if you have additional load, you need to get energy from storage, but then there are other times when you might have additional generation, and then you want, if you could curtail, you could, or you can put it back into storage, depending on what you might need. So this is a futuristic grid, and this is kind of a similar plot to the last one where you have power on the y-axis and hours on the x-axis. This is for a full year. For a futuristic grid nationally, and the 3 different things that are plotted is green or avocado looking stuff. That's your variable generation, just to kind of show how that varies over the year, which actually that's an amalgamation of real data because several wind and solar sites across the country and average them out. And then you have your base load, which is kind of down in dark blue, which sometimes is high, sometimes is low. It's trying not to change as much. And then you can see how the load is. I don't think anyone in this room is going to have too many problems understanding this. The big takeaway is sometimes your loads are really high, so no matter what you do, you're just not going to meet them. You got to have something else. You could either have a whole bunch of extra generation, which is expensive, or you can try and store it. Other times you have the reverse. You can either curtail or try and store it based on. So Dave, this gets a little bit to what's your criteria for needed. So this plot is a potential generation minus site use graph. Okay, I know it looks terrible.
That's not what I thought you meant by hot.
You're right.
Potential.
Potential.
That's good.
Yeah, that would actually look exponential. So this is gigawatt over hours, and around here. So my criteria is at every hour of the year, this needs to zero out. So if you're down here, you need to come from somewhere. If you're up above, you need to curtail or store. Okay, so this is kind of maybe a little bit boring, but basically the generation, so there's some base load and there's some variable specified as a mix between wind and solar, 80-20 roughly, I think, and then specify the percentage. For thermal storage, again, going back to trying not to be picking winners and losers, so I didn't try to pick things like, does it need to be distributed, or does it need to be integrated with an HVAC, or does it need to be, some kind of a PCM? All of that's sort of irrelevant. Model it as essentially you have a mass and power density and an energy density, but really that gives you a capacity and power in small plants. What kind of leakage rates do you have, and what kind of charge efficiency do you have? So this is the characteristics that would impact performance, and the notion would be, if you can get a handle on what things need to perform like, then you can give a kind of a goalpost or a benchmark to people who are doing research. Here's the kind of things you should shoot for. If you think you can reach them, then they can have impact. If you think these are completely unattainable, maybe you should not even try. And then there's this elastic other energy storage. You have a question? Okay. So this other energy storage. So I do everything I can on that one plot, potential generation plot, make it zero, using thermal. And if you can't, there are times you can't, then we have this magical backstop of other energy storage, which can provide whatever power and energy is needed, and I just keep track of that. And that remainder is essentially, maybe that is pump hydro, maybe that is batteries, that is some other technology that we're not dealing with that you need something. And Joe's not here, but anyway, he was hugely helpful in running all the red stock and a lot of the energy plus runs. And that's where all of the load data comes from. So the grid. This is simplistic, probably for a lot of people, but the current grid, if you look at some of these charts, if you're familiar with a lot of building loads, things like that, you might kind of have some rules of thumb in mind. But something to keep in mind here is that I switched all heating to electric. So everything came out of red stock, DOE, commercial prototypes that would have been gas, converted to electric with the COP. So loads are a little bit different than they actually are today. That's one thing to do for all, even the current grid. Peak to average capacity about 2, which is pretty realistic for some today, and around 8% comes from wind and solar. Okay.
My question is so you said you assumed the COP is 2 convert
Yeah.
to electric.
No, did I say that? No, I had a COP.
Sorry, so you assume the COP.
Oh, sorry. Yeah.
Sorry.
Sorry.
Okay. Yeah, know that. Did you also take into account the source somehow? If you go from gas on site to electric at a power plant, and then figure out what the bucket flow would have been, and then COP also like all those things? Or?
No, it was so. Once we got to the power plant, whatever I didn't go upstream with that with source energy. So it was you got electric to the power from the power plant versus gas. So whatever the COP. And for the gas, I just assumed that was site at the buildings, and I didn't really deal with transmission losses. And I'm like anywhere. So that's why I say my grid is somewhat simplistic. But really, you assume if you have your power plant, zero transmission losses, now everything's on site. So then that's the conversion that I did.
Okay, maybe I'll.
So if you have electric on site, or if you have gas on site, whatever the COP would have been to take that electric to serve the load instead of gas, that's what it is. Okay. So the future grid, similar, but a lot more aggressive in terms of the variable generation, between 70%, and I reduced this peak to average capacity or base generation. So the notion being, this is a lot more aggressive grid. So you're going to need a lot more storage in general. So just to kind of push the limits of what I have now. Realistically, I mean, 70% total production. I mean, people are talking about that kind of stuff. I mean, that's pretty out there, but it's not stupid things. So, control logic. So there's a lot of little stuff, but basically using thermal storage to the maximum extent possible. So I did not get into things like cost, because the thermal storage stuff doesn't even really exist, but that stuff kind of doesn't make any sense. But it was really, if you wanted to show what was the most you could possibly do with thermal storage, that's the way I looked at it. Keeping the grid stable, so that has to equal 0 on that one plot. And some of the control logic was to minimize this other energy storage. So again, a lot of things, all the results change completely if you have a different control logic, but the notion would be not only can you do the most possible with thermal, but the most includes minimizing what other things you might need, such as other energy storage plants, batteries, all types of stuff. And basically trying to balance that over the course of the year so that you're not sort of using extra energy to charge up your thermal storage system that might not be useful later. Sort of have to end and start at the same spot. And I guess, so I talked about the spatial control, about what that really means. That's kind of a big part. So if you look at this maximum spatial control, so I talked about this, I kind of jumped ahead. This is that theoretical minimum HVAC, roughly speaking, about 5 to 10% of what currently is used. And you see here, so this plot, I guess I should explain it. So this is quads of current heating energy and cooling energy. And then you have a kind of existing buildings and futuristic buildings. So this is one of the things initially looked at. So if you look at this plot, say, well, right now it's like 7.8 quads of heating energy right now. At these existing buildings, and you look at this theoretical minimum, you might be down around half a quad. And one of the things that people might say, and I question as well, is, well, how much does that change if you actually have a really good building? Like, should we really be thinking about making better buildings rather than this kind of ridiculous ultra zoning of people? And that would be if you look at these two bar charts. So if you look at existing buildings, you're around half a quad. If you looked at futuristic buildings, which these are things like R60 walls, CR20 heat pumps. I mean, they're not crazy ridiculous, but it's pretty advanced. And the picture that you get is not any different. The theoretical minimum is way, way, way lower than it is right now. If you have existing buildings, the theoretical minimum might be 5 or 10% of what's currently used. And if you have the best possible building that could exist, it might be 2% or 3%. Point still not the same. There's a lot of opportunity there. Not saying that we should go there. This is just kind of highlighting the boundary of what might be possible. And now if you were to look at the maximum temporal control, so this is when I say we have infinite performing thermal storage, this is 72% variable generation, but you have like 190,000 gigawatt hours of thermal storage, and and basically the 1 key rating you can charge and discharge that every hour. Right? Not limited at all by the performance of thermal storage. You're limited by your loads and what the needs are for everybody else. In that case, the metric that I use here would be the amount of other energy storage that's needed. So explain it, Louis. So this red circle, this would be existing buildings, so existing loads. I didn't deal with no changes there. But now you have a futuristic grid with 70% variable generation, which in general means you're going to need enormous amounts of energy storage somehow, right? Way more than anybody's going to think of that. If you did that, and I remember this also, these numbers end up being really large. Some of the reasons there because all of your heating loads are now electrified. So that does, you have existing buildings, it does increase your load quite a bit. But if you were to say I had no thermal storage, so I have this really advanced grid, huge amounts of variable generation, I need a certain amount of energy storage, which is a really, really large number. Okay. The reason that's important is because this other energy storage is kind of euphemistic for things like batteries, or maybe pump hydro or compressed air or something like that. But these are expensive technologies. They exist. People throw them around a lot. People talk about them. They're really, really super useful, and there's a lot of money going into development, right? Why would you even consider thermal energy storage? Well, if you did in this particular case, and you have the same scenario, same building, same grid, you added thermal energy storage, you could reduce the amount of this stuff by 90%, roughly. Okay. So then that's a big enough number that you might say, well, okay, again, I didn't deal with cost, but if you can reduce the amount of stuff, the amount of capital expenditure you need for this by 90%, this stuff can be, this is pretty cheap, which it might be. There's a lot of opportunity, right? We're not at that point. I'm just trying to highlight that there's a potential. So it's worth looking into further. And so here's an example, another situation that I looked at. So I took two different points here. One is kind of this intersection, what I consider kind of the best today building, and the other one is just the point up here on a futuristic grid. So you might be able to, with 70% generation, reduce your other energy storage by about 90%, reduce your base generation. So this is kind of euphemism for fossil fuel generation. It doesn't have to be, it can include nuclear and stuff. But basically, reduce that by 60%. These two here, one is energy storage capacity for other energy storage, 90%, and the power required from other energy storage, 70%. So, point being, thermal can do a lot, not just in existing buildings, even in advanced buildings. There's a lot of potential there. Now, those are all not limited by the performance of your thermal storage system. Okay. Now, when we try to get the idea of how do you kind of back off from that, and what sort of parameters or metrics for performance might you actually want to highlight or have people shoot for, we did a little bit of sensitivity analysis. And unfortunately, I did not have time to change the colors on these graphs because this is default Excel. But the colors in these bottom two graphs do not correspond to the colors in the top two graphs. That's unfortunate on my part. But what we're looking at in these bottom two graphs would be the thermal energy storage utilization factor. I'll explain in a second. And on the right would be thermal energy stored. And both of these are as a function of the power density of your material. So the idea being that if you have, power densities, these kind of need to be updated. And I do apologize for trying to finish everything. But this is really, for these power densities, you're looking at a 0.2 C rating. So if you guys think about batteries, it would take, with this particular thermal energy storage performance, it would take 5 hours to charge or 5 hours to discharge. I think I picked that as kind of a rough number. It's not as good as battery, but thermal processes are slow. So that might be a little more. But if you had a thermal storage system that might operate like that, then sorry, these two here. So then I'm sorry, I misspoke. There are two different energy levels, and then you look at the power density up here on this one, the power density here, and this will basically give you the C rating. So if you take this divided by that, with that divided by that, it'll give you your C rating. Basically, if you were to get up to 250 on this one here, you might get a 1 C rating. So these are still very slow. I'm not explaining this well, I apologize. But the point being is that there are limits to how much power you should try and get in and out of your thermal energy storage. Okay, that's the real point. When you get up here, you can still have a pretty slow performing thermal energy storage system, and you're not going to get like benefit by going much farther. Okay, people look at the thermal energy storage system. They look at capacity and energy density. Those are things that can reasonably well be characterized for a particular material. So they're kind of, as things go, easy to think about. People have done a lot of that kind of work. And I have to say on the next one, which I can talk about. It's more difficult to understand, like, how do you characterize power density? Because it depends on the rest of your system as well. And even things that touch your system, like how much you transfer out of air that's not even part of the system, things like that, from a wall, so forth. So the point is, you can quantify using this framework. You can quantify and say, look, if people are out here, we might actually kind of, roughly speaking, I didn't put this here, but you might be down in this like 5 or 10 watts per kilogram range in terms of current systems, might be down around there. So there's room for research. There's reason to do research. You might increase your performance, your impact, but you don't need to, if somebody came to you and said, look, I have something that can transfer 1,000 times as much power as current systems, that's great. It's totally useful. Probably not money. I don't want that money. Right? This is an idea for target things you might want to get from. Right?
similar to additional insulation.
Yeah, exactly. Very similar. And I'm trying to highlight that we have a way now of quantifying that. I mean, within the context of this model, you can get some ideas on what kind of performance metrics you actually might want to hit.
Comment back there. We didn't consider the space constraints of storage potential, like the advantages. You have a higher density, right?
Yes.
Potentially, there's for certain applications space.
Yes, that is true. Now, yep. Oh yeah, sorry. So the question was that I did not consider the practical considerations of space or weight and the value of that outside of the storage, right? And so that is true. So what I did do is to get the kind of baseline numbers for a lot of things that I ran. I had 1,000 kilograms per house with between 50 watt-hours per kilogram and 250 watt-hours per kilogram. And to make sure that those are sort of approximately reasonable, if 250 watt-hours per kilogram is similar in terms of performance to a lot of paraffin PCMs that are available today, kind of in that ballpark. So this is the kind of number that might be able to exist without too much problem. And if you have 1,000 kilograms of paraffin, that is kind of equivalent to half-inch drywall in an average house. So those are the reason I picked those is so that you wouldn't have outrageous systems like, well, what if I had 500 tons of PCM in my house, right? What can I do with it? You do that for the maximum, but for all of these other simulations, try and have things that would be reasonable, that would not be necessarily impressive. So you're right, I did not directly consider the cost or the value in that way, because in general, I didn't get the cost too much at all. But the numbers that you see here for a lot of these simulations, aside from the very limit from all the other simulations, I try to pick things that are reasonable and plausible. So 1,000 kilogram stuff, even if it's water, that's 1 cubic meter of water. Not saying that that is free in terms of space, but majority of buildings in the U.S. could probably have something like that. For example, your condenser outside your house on your air conditioner, probably about half that size, and then maybe a third. So things like this are kind of in the ballpark of reasonable. Yeah.
I'm having trouble reconciling the two big concepts that you've talked about. One of them being very personalized, very targeted heating and cooling, and thermal energy storage, which to me are not.
Really, those are different.
They don't seem to mesh.
Well, so that's why, in some ways, that's why they're orthogonal. If they did mesh, they wouldn't be independent necessarily. So, but fundamentally, there's not necessarily a reason why energy that is provided in a very localized fashion could not also be stored. So, you do have to abstract yourself from current buildings, right? In order to accomplish this, things are completely different than they are now. That's by definition why current buildings are down here in this corner where things don't change that much, right? Things down there work. You want to change dramatically? You want to look at 66 quads and say, what can I do with it? Is it practical now? Absolutely not. Totally absurd, right? But we're not. But this is a big idea. This is not incremental improvement. You want incremental improvement, you go from 15 to 20, right? This is totally different. I don't know if that makes sense.
I'm not sure I'm convinced that it's possible for you to basically make up all of the heating and cooling needed in building, all the thermal energy requirements entirely from thermal storage, and localize all of that to be very person-specific.
Right now, it's not possible. But
no,
you can hold on. Good.
Have a microphone.
Yes.
This sounds good.
It is. And people can hear it incorrect. So the Bethany's question, I think, maybe looking at it the opposite way as well, because there's two ways you could focus. You could go, and recognizing that there's trade-offs to both. You could go 100% and only focus on efficiency potential, and inherently, you're not going to have as much energy to be flexible with, right? If you have a little energy, there's little to be flexible with.
Or you can say, well, I'm going to maximize energy stored, but then if you do that, you're going to have to utilize energy. So there is an inherent, that's why there's a somewhat of a trade-off where at maximum total energy going through the thermal storage, you're not going to have the maximum, you can't have both. And so it's really to illustrate that trade-off, but then not being constrained by the trade-off, because there is a lot of opportunities to do both. Right now, I would argue that in the past, we only focused on the y-axis and totally neglected the opportunity on the x-axis. And so now, but you can't just go 180 if they were on there, totally focus on the x-axis, because then you would waste a lot of energy. So this is kind of the guide towards what if we did both. There's still a lot of space if we consider both. Does that reconcile? Because there is an inherent trade-off. We're not, and we didn't want to, we have to be careful. We're not saying that we want to use more energy to be flexible, but there are scenarios in a dynamic and distributed grid where flexibility has a priority, and how can you do both in those cases?
And maybe one other thing is the farther, I mean, this is obvious, but the farther you go away from this little blue box, the more preposterous the technologies need to be to actually accomplish this. And that's known, and that's okay, because remember, this is a big idea, right? Is it actually, like, from a thermodynamic point of view, is it possible to get up here? Yes. Is anyone ever going to develop that technology? Well, I don't know. Probably not. NASA sort of does it. They have spacesuits, right? Oh yeah. See, now you're getting away from here. I totally understand that these things are preposterous. They don't exist. It's not. I'm saying like, oh, it's no big deal. I'm talking about like as a thermodynamics that's gonna like prohibit. And beyond that, they're kind of. Yeah, there has to be a willing suspension of disbelief. This is not about like incremental improvements, even large incremental improvements. Like this is a complete paradigm shift of how things like that happen.
It's difficult to imagine.
Yeah, you have to really abstract yourself from reality.
Or you have to only be limited by thermodynamics.
Yeah,
that's what the theoretical potential is. You're only limited by the laws of physics, not limited by what our current innovation.
Yeah. What currently exists? What do people like? How much does it cost? Yeah. I mean, we're trying to constrain it a little bit beyond thermodynamics. Like we want people to be comfortable wearing the same kind of clothes and doing the same kind of things. So there are some constraints, but
for the most part, the thermodynamic limit is those are thermodynamic limits. That's why there's such a gap between current and thermodynamic. But if we were fully creative and only guided by the laws of physics, what could we do? The argument is we could do a lot more than we can do.
So to follow up on that slightly, so when we hear we're saying, well, look, the theoretical minimum is 90% energy savings. ARPA-E, y'all know about ARPA-E, they were targeting like 20 watts of personal cooling rather than 100 watts or so. So even ARPA-E was looking at something down around a year to give you an idea of how far out it is, and it's not limited. But okay, so I think this is my last graph. This is very similar to the last one about power density. This is looking at how do you try and quantify performance targets. This is looking at energy storage. So here, actually, I'm on the same plot, but there is total energy stored, which is blue, and there's a utilization, which is basically the total energy stored divided by the capacity of it. And the notion is, as you increase energy storage, yes, you can continue to store more energy, but you're doing it less efficiently. You have to add mass a lot more than you're going to add storage. So at some point, they're kind of diminishing returns. Nothing super difficult there, but we can quantify like that solution. Like inflation. Yeah. What's your thing with inflation?
All right, I like time. He's got the right y-axis here.
Yeah.
Is that over a year? Or what is that?
Yeah, it's over a year. So you take whatever, here you have big energy storage density, multiply that times the total mass. That'll give you capacity of thermal storage. Take this over divide that.
And you're assuming that the same thermal storage can be used for any thermal load.
Yeah, I only have one thermal storage and it has one performance. Yeah.
What about refrigeration?
I not included refrigeration. I have heating, cooling, and water. I think. Okay. Summary. Spatial is really, really large. It's worth. I think what we're trying to do is to show that this is worth investigating. We're not trying to show that this is practical. We're just trying to show that the opportunity space is big. You should think about it. I think we're also trying to show that the problem that we're trying to address, or that we're trying to deal with, which is going to get worse as you get more and more variable generation on grid. And there are alternative solutions. There are things that are practical, okay, but they're expensive and they're high demand. And so you should at least, I think, consider this. The other thing is that this is well beyond traditional approaches. Nothing at all like incremental. Trying to think big here. And it's going to take a long time. A lot of this is this is ground up technology development. It's a complete paradigm change. It takes a long time. So if you're going to investigate, you try to start sooner than later, otherwise you're going to be behind the ball. And then you're going to have suboptimal solutions that cost tons of money and take a lot less resources. Okay. Oh, and it's likely, this kind of is what it is. Likely, even though I model single sort of performance characteristics, right, that it's going to take multiple solutions. If you were even going to try and use any of these approaches, it's probably not a single one size fits all. Okay, Marcus.
Good question.
No, it's not.
It's not on.
No, it's not quite.
Okay. I cannot avoid thinking about the reject heat of thermal electric power plants. Given that 70% renewables increase from 30% to the rest, you have 70% of reject, kind of, right? So the efficiency of the thermal electric power plant is about 30% or so. 70% is least rejected, right?
Mm-hmm.
There's a lot of heat there, right?
It's high quality relative to building.
Well, for buildings, this is my point. For power generation, it's really low availability heat, right? So from a thermodynamic standpoint, it sucks. Mm-hmm. But for a building, it's precious, right? Because that's hot enough, temperature-wise, that you still can do quite a bit in buildings. Did you give any consideration for thermal storage for that heat reject as connected to this?
No. So initially, this is focused on the building side of things. So that initial plot, there was the power generation, transportation, industry, and building. And so we were tasked with building. So there's no doubt. So heater's bigger than just this project. There's no doubt that people are looking at that or should look at that. I mean, in general, if that were easy, it would have already been solved. So that's also a big idea, way out there kind of thing. But that was beyond the purview of this particular project.
I think the planting that I'd like to make is the fact that for power generation, that is useless, or pretty much, right? But for buildings, and that's the connection that I'd like to make, that's actually pretty precious, or it could be. It's mislocated.
Yes.
That's a problem. It's a mislocated heat, but it could actually help you quite a bit if we actually think creative. You already posed that we need to think creative, enough. So what about thinking creative about like the reject that we have in power plants to use it?
Actually, I have a piece of paper on my desk where we were thinking about that at the very beginning.
I have no idea.
Yeah. No. I don't want to say I solved that.
Oh.
I didn't solve it. I'm just saying I think it's a good idea. I don't know what to do about it beyond the.
There's 1,000 ideas if you go look at papers from the desk.
Yeah, that's true. Yeah.
Co-locate your buildings and your power generation.
You don't want that. That's
undesirable, right?
Yeah.
Very undesirable.
The fundamentals, okay, I mean, there's a lot happening.
Really a bad thing. The pollution problem. The pollution problem. Well, we can solve that. That's another. That's another solvable problem.
To get rid of your power plant.
Well, but you still have 30%.
Yeah, sure. That's what I'm saying. It's sort of like you're planning for the grand future. Why?
From 100%.
Sure.
Okay, well,
We're thinking future, right?
I can model that too. We have one more question for us. Last one.
Just thinking of like, viability in the longer term. I mean, it seems that like Rankine cycle power generation is on its way out just because renewables are getting so cheap. And I see a lot of our building technology that we're developing has to compete with this ever cheaper renewables and energy storage being a lot cheaper. So I'm wondering where you see thermal energy storage fitting in that race. And do you think that we can, solve some of these variable renewable energy issues fast enough at a cost competitive enough way to actually compete with the increasing prices of renewables?
Yeah, so actually, if I were to guess, I got my crystal ball out, and the project is crystal ball. You're going to get to high penetration of renewables way before you have cost-effective, large-scale thermal storage of the kind we're talking about. So in the meantime, in my opinion, you're either going to overbuild either in terms of renewables so that you can so you never need storage, or you're going to keep a lot of existing power plants available for peaking so that you can do the same thing. That's probably going to be a medium-term solution. Or other energy sources, batteries and things like that, are still going to be pretty darn expensive. It's probably still going to be cheaper to just keep extra power plants online for that before other technologies go. That's my personal opinion. I don't have anything to back that up, but I would think that's exactly right. You're going to get the one a lot sooner than the other. Problem. Okay, we're done.
Yeah, and so thank you guys for coming. Thanks, Chuck, for speaking. I know Roderick's going to say a few words, but I just want to remind you, we started this because it really isn't meant to be just a presentation. We want this dialogue. So, yes, thanks for putting them on the hot seat, but we want to encourage you. If you have topics that you want to share too, please volunteer these up as we start trying to plan these every 4 to 6 weeks. So, Roderick, go ahead.
No, and thank you all. This is very helpful because when you're trying to present a different way of looking at something, the communication is the trickiest part. So this is super helpful for Chuck and the program because to answer the question that was just asked, most of the research on battery storage, if we really believe that clean energy technology is important, if you look at the market is investing in electrical storage, not for stationary applications. Most of the research is going into transportation. And so if we do want a renewable world, there's no storage available right now. The companies, the batteries and savings, those companies that are making battery storage are investing in electric transportation. So if we don't have thermal storage options, you can make the logical jump. What happens through all the research that we're doing for renewable energy? It gets way too expensive to cost effective. So how do we do this? That's the point. We don't know. So if you think of more options, please hit Chuck and ways of communicating. Because if we don't, this is really a call to action. We don't start thinking about different ways of managing heat and storing heat, and we only resort to, well, the battery people will figure it out. Talking to the battery people, the world that they're looking at right now is all about mobile storage. And the whole way they do that doesn't work for space. So we need building solutions. Thank you. Thanks, everybody. Thanks, Chuck.